morning, students. This is Dr.GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. In this session, I would like to explain about mechanical properties of engineering materials. So, what are the mechanical properties, and then what is the importance of mechanical properties in mission design? We will see. First of all, introduction about the material properties. The practical application of engineering materials in manufacturing engineering depends upon a thorough knowledge of their particular properties under a wide range of conditions. The practical applications of any engineering materials, so manufacturing engineering design, that depends upon this knowledge of their particular property. We should know the properties of material while designing any component or product. If you don't know the particular property of a material, so ultimately the design will be fail. So which material is suitable for which component? So how to measure these properties while testing? Is it reliable or not? Whether it gives good strength or not. So we have to check all these conditions, all these parameters while designing a machine component. So that's why you should know about material properties. First you should know about engineering materials, and then what are the properties important for our particular product. So the term property. So what is this property? The property is a qualitative or a quantitative, the measure of response of materials to externally imposed conditions like forces and temperatures. It is a qualitative and quantitative measures of response of materials. So whenever the component or the material subjected to particular force, it may be tensile or it may be compressive or shear. So what is the response of that material? Similarly, whenever the component is subjected to some temperature at 100 degrees centigrade, in that conditions, what is the material response? You should note that is called as property. So suppose you applied force on one component. So suppose whenever you applied force, then it elongates. So that means that material having elasticity property. So however, the range of properties found in different classes of materials is very large. So I will tell you one by one all these properties. Today we will discuss one by one. The properties of materials are generally classified into mechanical properties of materials, and then physical properties and chemical properties. The mechanical properties of materials are like strength, toughness, hardness, ductility, elasticity, fatigue, and creep. These are important properties. The physical properties are density, specific heat, melting and boiling point, thermal expansion and conductivity, and electromagnetic properties. All these properties comes under physical properties. So third one is chemical properties. So the chemical properties are oxidation, corrosion, flammability, and toxicity, etc. All these properties comes under chemical properties. So now we will see, we will explain, we will study about mechanical properties of materials. What are the mechanical properties? How to measure these property? So what are the applications of these properties? We will see in this session. The properties of material that determine its behavior under applied forces. Already I told you, whenever the component or the material subjected to some particular force or temperature, so how it behaves. So what is the response of that particular material are known as mechanical properties. When applying load, so these type of properties are mechanical properties. They are usually related to the elastic and plastic behavior of the material. You know, elasticity property and plasticity property. These two also comes under mechanical properties. These properties are expressed as functions of stress and strain. It's a very, very important. Properties are expressed as functions of stress and strain, etc. So, what do you mean by stress? What do you mean by strain? How to calculate the stress? And how do you measure the strain? So I will discuss in next slide. A sound knowledge of mechanical properties of materials provides the basis for predicting the behavior of material. If you know the mechanical property of the particular material, you can predict the behavior of material. So under different load conditions, so suppose you are applying load, tensile load, how it behaves, you know. So why? Because the property is already studied. Clear? While designing of the components. All these properties you should consider. Stress and strain. The experience shows that any material subjected to a load may either deform or heal or break. Sometimes some materials behaves in deformation, and some materials healing, and some materials will fail. Depending upon the one is magnitude and then the nature of the material and the cross-sectional area of the component. What is the magnitude of the load? How much load acting on that particular material? And what is the nature of the material? And the cross-sectional dimensions of the component. So the sum of the total of all these elementary interatomic forces or internal resistance which the material is called upon the exert to counteract the applied load is called stress. So whenever the component or material subjected to some load, so some interatomic forces or internal resistance force will be developed inside the material. That is called as stress. See here, mathematically the stress is expressed as force divided by cross-sectional area. So take here the shaft across a circular rod subjected to tensile force. Clear? So this is the cross-sectional area of the rod. So you can calculate the stress is equal to force upon cross-sectional area. So here shown 3D diagram, rectangular bar subjected to axial tensile load. These all are load carrying lines, the force carrying lines, uniformly distributed from one end to another end. This end to this end. Why? Because this is a uniform cross-sectional. Having uniform cross-section. So you can calculate stress by using this relation, force upon cross-sectional area. Strain is the dimensional response is given by material against mechanical loading or deformation produced for unit length. How much deformed when it is subjected to tensile load or compressive load? That is called as a strain. The deformation produced for unit length. See, in this diagram shown, this bar is subjected to tensile load. This one, previously the dimensions are length and a cross-sectional area. After deformation, it elongated. How much? This is delta. How much deform? So this is after deformation, length and original length. So you have to measure what is the change in length. So mathematically, strain is a change in length divided by original length. How much deformed? The change in length divided by original length. It gives strain. So here you can see delta L by L naught. Here in this case, the strain is equal to delta by L. Now, the important property, the mechanical property of engineering material is strength. The strength of a material is its capacity to withstand the destruction under the action of external loads. So if you want to design one component, mechanical component, it is subjected to tensile load. In that case, it should withstand the load. So it should capable to carry the load. It means its capacity to withstand the particular load. So that property is called as strength. It determines the ability of material to withstand stress without failure. Without failure, it should withstand. Suppose one component is there. So rectangular bar, the load is acting 20 kilonewtons. So without failure, it should withstand this 20 kilonewtons load. It means having that capacity. So behind the 20, suppose 30 kilonewtons applied. It does not withstand the load. So why? Because this is the maximum load. The component will fail. So the maximum stress that any material will stand before destruction is called ultimate strength. The maximum strength, ultimate strength. See, in this diagram shown, this one. So here, we are applying force. By applying force, you can bend, or you can separate this component into two pieces. You are applying load 10 kilonewtons or 5 kilonewtons, whatever load you are applying on this component, it should withstand this your applied force. Then only it's you can say having that capacity. See, in this, a load acting tensile load. These two men are fully. They are applying load. So the component should withstand the external load without failure, without breaking. How much load withstand? That is called a strength of the material. Then only you can say this component withstand up to 20 kilonewtons. this component is withstand up to 50 kilonewtons. It means beyond the 50 kilonewtons, the component will fail. Next property, elasticity. So the property of material by virtue of which deformation caused by applied load disappears upon removal of load. So suppose one component is subjected to tensile load, immediately you remove that load. What will happen? So due to that first load, some deformation will appear. Whenever you remove the load, then it goes back to its original position. That type of property is called as elasticity. Elasticity of material is the power of coming back to its original position after deformation when the load or stress is removed. This type of property is called as elasticity. Example for this elasticity property, spring. Spring material having this elasticity property. Rubber. See, in this diagram shown the elasticity property. So in this, the first one, the molecules are arranged in systematic manner, and then apply load. Here some force applied on this component. So this is a one bar, so fixed at one end and other end is free. So due to this tensile load, some elongation will be occur. So that is deformation. So some disturbance due to this load, some disturbance will be occurred in this bond. The bond will be stretched. So return to whenever you remove of this load or stress, then immediately it goes back to its original position. See this diagram, returns to its original position. So again rearrange their molecules as first one. This type of property is called as elasticity. The elastic means reversible. So in this diagram, force versus elongation, you can see linear elastic is a straight line and non-linear is not a straight line. It is a curved line. Why? Because in a linear elastic, the force is directly proportional to deflection. It means stress is directly proportional to strain. Next, another example. So before loading, the spring is like this, and during loading, it's somewhat compressed. Yeah. So what is the free length after load is removed? So there is no change. So it goes back to its original position. So this type of property is called as elasticity property. So you can measure strain, change in length by original length. So you can calculate Young's modulus by using stress and strain. Stress directly proportional to strain, you can write in terms of Young's modulus, elastic constant, E into C, epsilon. So Young's modulus is equal to stress upon strain. So here you can see the change in length. That is, you can represent with delta L. Next property is plasticity. The plasticity of material is its ability to change some degree of permanent deformation without rupture or failure. So it means the plasticity property is opposite to the elasticity property. Whenever you remove the load, so it goes back to its original position. But in this case, not like that. The permanent deformation will be occur. The plasticity of material is the ability to undergo some degree of permanent deformation without failure. This position is called yielding position. The plastic deformation will take only after the elastic limit is exceeded. Up to elastic limit, the stress is directly proportional to strain. The force is directly proportional to deformation. Beyond this elastic limit, the plastic deformation will be occur. After this plastic deformation, if you keep on increase the load, then what will happen? The component will fail. Rupture happens. Next, it increases with the increase in temperature. This property, if you increase the temperature, the plasticity property also increase. So example, plastic. See in this diagram. So this is one bar attached fixed at one end and other end is free. It is subjected to some external load. The bond stretch and flames undergone shear. The elastic plus plastic. See third one, the plane still sheared. After removal of load, here there is no load. After removal of load also, it is in a plastic deformation condition only. So that is called as, this type of property is known as plasticity. So here shown diagram, the linear elastic versus plastic deformation. The plastic means permanent. So linear elastic, up to linear elastic there is no change. The force versus the plastic deformation. After this elastic limit, the material undergo plastic deformation stage. Next, stiffness. The resistance of material to elastic deformation or deflection is called stiffness or rigidity. So the material should withstand resistance of the material to elastic deformation or deflection. So it means a material which suffers slight deformation under load has a high degree of stiffness or rigidity. Example, steel beam is more stiffer or more rigid than aluminum beam. The stiffness of a spring. Load for deflection. How much deflected? So when it is subjected to some particular load. So that property is called as stiffness. Next one is ductility. It is the property of material which enables it to draw out into thin wires. So example, mild steel is a ductile materials. So you can draw the mild steel material into thin wires by applying the forces. So the percent of elongation and the reduction in area in tension is often used as empirical measures of the ductility. So you can measure how much percentage of elongation will be occur, how much reduction of area. This is the measures of ductility. So see in this diagram, this component starting position subjected to the ductility property. So after some time, what will happen? It drawn into thin wire. This is end point. So after this point, the component will fail. Up to certain stage only, it will elongate. So due to the ductility property, So the ductility property, example mild steel and aluminum, um, this and gold is the ductile materials. See in this diagram, the tungsten carbide die is used to elongate this the copper bar. This copper bar is pulled through the die and its diameter is reduced. The previous diameter is this much, and after reduction of area, the diameter is changed. You can use another tungsten carbide die, and you can draw into very small wires, small diameter thin wires. This type of property is called as ductility property. Next, malleability. The malleability is material is its ability to be flattened into thin sheets without cracking by hot or cold working. This one also ductile property, but not into, you can't draw into thin wires. So the ability to be flattened into thin sheets without cracking by hot and cold working. Example, the lead can be readily rolled and hammered into thin sheets, but it can be drawn into wire. See in this diagram shown, the gold is the most malleable metal. Malleability, metal hammered into thin sheets. See, you can see this is the original raw material of the gold, and after this due to this malleability, so after hammering you can convert into thin sheets. So due to this property, the malleability property, all gold raw material of the gold converted into the various ornaments by using hot working and cold working. Next one is resilience. So it is the capacity of material to absorb energy elastically. So how much energy absorbed during that particular load? The maximum energy which can be stored in a body up to elastic limit is called as proof resilience. And the proof resilience for unit volume is called as modulus of resilience. So one is proof resilience and another one is modulus of resilience. The first one is the maximum energy which can be stored in a body up to elastic limit, that is called as proof resilience. And the proof resilience for unit volume is called the modulus of resilience. The quantity gives capacity of the material to bear shocks and vibrations. Next, you can see in this slide resilience property diagrams. So how much energy stored while it subjected to load. So you can see in this in the spring. This property is essential for a spring material. So how much energy absorbed during under unit volume? So yes, load is 10,000. So what is the resilience percentage? Apply load and release. How much energy stored? So by using this empirical relation, you can calculate the resilience percentage 100 by HR by H0 minus 1. So what is HR shown in this diagram? Next, hardness property. So this one also very important for engineering materials. Hardness is a fundamental property which is closely related to strength. The strength property and hardness property are both same but closely related. But hardness is usually defined in terms of the ability of material to resist to scratching, abrasion, and cutting, indentation, or penetration. Methods used for determining hardness are Brinell and Rockwell and Vickers methods are there for testing purpose. How do you measure the hardness of particular material? So what is the hardness of a this steel? Hardness of the diamond. Various methods are there to determine the hardness property. So it is the main the property, the ability of material to resist to scratching, abrasion, cutting. The hardest material in the world is diamond. See, in this hardness tester, the mineral on mineral and then knife. This here you can see the fingernail and penny and glass. Clear? These all are examples for hardness property. Whenever this material is subjected to load, you should not give any scratching, any abrasion. So that then you can say this material having this much of hardness. Next, brittleness. It is the property of breaking without much permanent distortion. Non-ductile material is considered to be brittle material. So non-ductile materials, ductile materials are mild steel and steel. So by example, glass, these the brittle materials are, non-ductile materials are glass, cast iron, etc. It does not give any the indication before fracture. Suddenly the component fails. This type of property is called brittleness. The property of breaking without much permanent distortion. In the case of ductile material, first deformation will be occur. After that component, after next stage, after deformation, the component will fail. Next, creep. The slow and progressive deformation of a material with the time at a constant stress is called creep. This property is important for belt drives. The slow and progressive deformation of a material with time at a constant stress. Depending upon temperature, stresses, even below the elastic limit, can cause some permanent deformation. It depends upon the temperature and stresses, irrespective of their elastic limit. It causes some permanent deformation. It is most generally defined as time-dependent strain occurring under stress. See, you can see in this diagram the creep property. This is a specimen. So heating element, the thermocouple is used. The constant force applied. The extension measured over gauge length. Here constant force, there is no change of force, there not gradually increasing the force. Measure is subjected to temperature with the help of the thermocouple, give some heat to this specimen. So measure that extension. This property, creep property. Next one is fatigue. The last property. This phenomenon leads to fracture. Very, very important property in design of machine elements. Fatigue. So always all the components are subjected to fluctuating loads. So whenever the component is subjected to cyclic loads, after some number of cycles, the component will fail. At which the component fails below the yield stress. That strength is called as, that limit is called as endurance limit. This type of property is called as fatigue property. The phenomena is called as fatigue fracture. Under repeated or fluctuating stresses, this phenomena happens. Fatigue fractures are progressive beginning as minute cracks and grow under the action of fluctuating stress. So initially, the small cracks will be induced. That the very minute cracks. After increasing the load, they grow under the action of fluctuating stress. Fatigue fracture will be happen. Many components of high-speed aero and turbine engines are of this type. Our IC engine components always subjected to this fatigue, the fluctuating loads. Crankshaft fails due to this property, fatigue property. See, in this diagram, the surface of a fatigue fracture shown, the granular surface and rubber surface and the origin of fracture. You can see under the microscopic test. These are the specimens. The standard specimens, these are polished specimens. You can test the fatigue property by using fatigue testing machine. You can calculate the number of cycles to failure and the fatigue strength. So this way the mechanical properties of engineering materials is very, very important while designing a machine component. These are the important the properties. You should thorough knowledge of these properties. Without knowing these properties, you can't design any component. You can't apply force on that particular material. These are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.